So if you look at your lab experiments, I'll use experiment number 5, your back titration, the determination of the percentage of ammonia in household ammonia, as a particular experiment that we can look at to do this whole lab test. Okay, so whenever you go to an experiment, whenever you're doing your lab, you know how you start your experiment by simply writing the whole title of the experiment. You need to know the aims, the objectives of what you're going to be doing. There's that part where you have the introduction, they tell you about the apparatus, there is the whole discussion that you write, then comes the data collection, then the data analysis, then you have lastly the summary that you're supposed to give. To mention the number of ways that the experiment can be improved and so on and so forth. So in a lab test, everything is going to be taught to you. They are going to explain to you what you're supposed to do. So they're going to be a set of rules. They'll give you a leaflet that is going to have or contain all the instructions. Not really in particular whether they'll ask you to go with your lab manuals for them to pick any of those experiments from there, but they will communicate. So the rules will be given to you, meaning the instructions, each particular step, everything you're supposed to do. Yeah, so step by step. You just have to follow the steps and also make sure that you have all the apparatus that are needed, that are relevant for, that they will indicate in the whole thing. They'll list them. So you need to make sure that on your station you have the apparatus, everything that you need in place. And it's calibrated, you have to rinse them. So all those rules, everything else, they will be observing you. Obviously, things like you being in a proper outfit, those are obvious things that you know already. Your safety boots, your goggles, everything else. Yeah, so the rules will be given to you, the instructions. And all the apparatus are supposed to be in place. The solutions, if you need, or there will be need for you to collect from the lab technician by the window there, already primary standard solutions that are going to be produced, you have to do all the proper collections. So everything is set for you. Yeah, so let's just run through everything as the document is still loading. Then if you're doing your back titration, we're going to take the best case scenario that they give you, experiment number 5, as experiment that you should expect, but they can give you anything from the labs that you've done. That's what a lab test is based on. Yeah, they'll not bring something that you have not done before. So even the answers you're going to be getting are still going to be in the same range. So if they bring experiment number 5, they're asking about observing or rather identifying some certain substance. In this case, you want to find the percentage yield, right? Meaning the percentage yield that you got in your lab experiment is almost going to be the same with what you're going to get in the lab test as well, because it's the same thing. They just want you to do it alone, for them to just be certain that you are following and you are participating in the whole process of all the experiments that you are doing. Yeah, that's what a lab test is all about. Yeah, so they will give you everything you need. That's the rules, the apparatus. They will tell you what to collect, what to mix, and how to mix. So like in experiment number 5, I'll use the discussion there, how the materials, the chemicals, and the procedure which was given. They said standardized hydrogen chloride. So I'm using experiment number 5. I've skipped straight to part 3 from your lab manual, the part that says procedure, which is part 1. They want you to standardize hydrogen chloride and sodium hydroxide solutions. The technicians will provide you with concentrations of HCl and sodium hydroxide solutions. That's part 1. So obviously you have to make sure HCl and sodium hydroxide are there on your station. You collect them from that side, and then you make necessary dilutions to have enough so that you can repeat your titrations to get a certain number of trials for you to get a mean titer. Yeah, so when you get your standard solutions, you need to get your standard solutions. They may ask how or what a standard, how to make a standard solution a primary. We'll look at the questions later on from the samples I provided. So you need to collect your standard solution from the technician, then you dilute them using your distilled water to make up to some volumes. Mostly it's 250 mils, depends on the beaker that you're going to be using. But the procedure will still stipulate. Yeah, so part 2 there, they're saying determination of the concentration of ammonia in household ammonia. So they are giving you the instructions. They're saying pipette 5 cubic centimeters of ammonia solution. So you do the pipetting, everything that you do. You use your pipette, you collect 5 centimeter cubed of your ammonia solution into a 250 conical flask, and you pipette 25 of 0.1 hydrogen chloride. So on the board, they are going to write the concentrations, because these are just numerical values that they are going to attach to the solutions that you are going to be using. The volumes are going to be given to you in terms of your measurements, but the concentrations have to be written down for you, because these are just theoretical values that we need for us to do our quantitative analysis, like in the calculations and everything else. So I'll go straight to your end of your procedure, like after you follow your experiment, because here they've given us, I'm using this example, you have sodium hydroxide. They will tell you how much of this you are getting from the lab technician, because these are in small proportions that side. So you get, let's say, 0.5 molarity. That's their concentration. They just tell us. They will tell you to get, let's say, 5 cubic centimeters. Then once you get this, you dilute it, put it in a 250 milliliters or cubic centimeters vessel using, we're adding water. So we added water. Yeah, you add water. The reason why we're adding water is so that we can have enough sodium hydroxide to run as many trials as possible. The same applies to your HCl. You're going to have something like, here they're saying what? They're saying we have 25 cubic centimeters that you put in your pipette, whose concentration will be given to you, which is this HCl. They will state, if you won't carry your lab manuals, meaning they'll give you the values on the board, they will write them out so that you use them in your calculations. So in this particular case, we know the HCl that we are using. What we were trying to find out is how much volume is needed for the sodium hydroxide, how much volume is going to be needed to neutralize this particular acid, 25 in particular. Yeah, so we are running trials to find out the volume of sodium hydroxide. We always add the what? We always add the base to the acid, because the reaction is a little bit manageable. It's not as explosive as it would be if we were to add the acid to the base. So that's the other reason. So when you do your trials, from your, let me just put it up here. Yeah, so we're going to go to experiment number 5, which is your back titration.
Come to the screen.
Okay, just a minute. Yeah, so like I was saying, these guys know that you do copy and paste when it comes to instructions, the summary, the title, everything else. You do it as a group, or if you have a lab partner, they know you always have a way to work around the discussion, the qualitative part when it comes to the description of what happens in the experiment. So here now we want you to give us the quantitative part by you doing the data collection and the calculation. So this is from what I was explaining, from the procedure that they're going to give you. So I've done this experiment, this titration. In this case, they were using HCl and sodium carbonate. So they simply reacted the acid and the base, the carbonate, the metal carbonate. They did 3 trials. Of course, you know to say the trial run is never going to be accounted for. We don't need it, or we never use it in the calculation of the mean titer, the average. We only focus on the actual trials, because the first one just gives you an approximation for you to know the end point of your experiment. Yeah, so this is what they did. This is what you have. Yeah, so I'm going to be reading the questions from the images that were sent. So after the procedure and the data collection, there are only like 5 questions at the end there. They're saying calculate the moles of sodium hydroxide. In this case, it's going to be potassium carbonate, because this is what we are comparing with our acid. So it depends with what you have, and make sure that before you do your calculations, you have a proper equation. A balanced equation is always vital for your calculations, because once your equation is not balanced, meaning all the calculations you're going to be doing are going to be wrong. And in an event where they don't bring a lab that you've done before, so all I'm saying for this particular part, for those that are just going to access the recording, is that please go through your lab manual, focus on those titrations, or rather experiments that involve titration, both forward and backward, especially the redox one. You can do the redox one or the chemical kinetics experiment. Yeah, so they'll be rotating depending on the group that you're putting, they'll be rotating the experiment. They won't be repeating the experiment. So those that are going to do the experiment tomorrow, even if you share it with your friends, it won't be the same with the guys that are going to do it on a Tuesday or the other day. They'll be rotating the experiments because when they announce, you just go there blank. They just explain to you, oh, we're doing this experiment. So you have to be ready for all the experiments, all the types of calculations in terms of data collection and data analysis. That's the only part that they're interested in. Yeah, so I won't waste time with this because you do have the crooks, meaning you are able to solve such. So let's look at these sample questions that I forwarded. I'll start with this Chem 1000 because everyone here, apart from Joseph, I think they're doing what Chem 1010. Yeah, so look at this experiment. They're saying answer all questions in the provided separate sheet. The duration here was just 30 minutes, so it depends. Here they were just strictly questions that we're asking. So look at the question, the first one. They're saying calculate the percentage uncertainty of 100 cubic centimeters volumetric flask with uncertainty of 0.2 centimeter cubed. The way we go about it, yes. So this is going to be part of the stuff you need to go through. In your lab manual, there's a part of errors. Yeah, the first part in your lab manual, when it comes to the instructions, the safety, in between the safety there, I think there should be page 5 or something. So the percentage of uncertainty here is simply going to be the uncertainty given, which is 0.2 cubic centimeters over the volume given, which is 100, then multiplied by 100. So that's how you get your percentage of uncertainty. So this is just going to give us 0.2 cubic centimeters over 100 cubic centimeters, then multiply this by 100%. Yeah, so we'll have this part here cancelling with this part here, the 100. This should give us 0.2. Yeah, the correct answer here should have been 0.2%. The answer here was supposed to be D. That's what you have. So you see how they can phrase the questions. In as much as we've said it could be anything from your lab manual, even errors, how you go about your calculation, the best fit line, they can give you to plot a graph and ask you to just, let's say, get the gradient to draw the baseline of it. All those things that are there when it comes to how we carried an experiment, the things before. It could be conversions, units. Yeah, so you really just have to go through your lab manual, everything else that you've covered so far. The next question here, they're saying, this is mostly for those doing Chem 1010, but they can ask it because you do have it, even those guys doing Chemistry 1000. The second one again is the same. They're saying a volume of 50 cubic centimeter burette with uncertainty of 0.05. It's the same thing. We're going to do the 0.05 over 50 then times 100. Yeah, so question 1 is going to be done in a similar way. This was based on errors. They are saying the uncertainty of 0.05 cubic centimeters from a volume of 50 cubic centimeters. So we're going to carry out the similar thing, the similar calculation, the uncertainty over the volume times 100%. It gives us the percentage of uncertainty. So this is these are given in cubic centimeters. The good part is that errors are dimensionless because the units always get to cancel out in your calculations. Yeah, so you have, this is going to give us what here. So don't trust the answers that are in bold or in black, in dark black, because there could have been errors here on this mark scheme. What answer do we get here, guys? Anyone with a calculator? Yeah. 0.1%. Yeah, so our answer here is going to be A. Right, so we get our A. That's going to be your answer. That's the formula. So you see, this was very much erroneous. So this would have been our answer. The answer is A. Look at the next one. The next one, they're saying a chemical reaction of a 0 order when the reaction rate is where the Ca, which is the concentration of the reactant, a chemical reaction of orders of 0 order. When the reaction is, so they're saying a chemical reaction is of 0 order when the reaction rate is what? So if it's a 0 order, we say the chemical reaction the chemical reaction, the rate of the reaction, in short, is simply equal to the rate constant. Remember, if you have a zero order reaction, this is your differential rate law, right? Looks like this. Yeah, so we're saying the rate of the reaction is going to be equivalent to the rate constant. That's the first thing we know about a zero order reaction. Yeah, so we're trying to relate whatsoever we have. So here they're saying when the reaction is, which answer here, guys, is going to be befitting the last part of our statement. A chemical reaction is of zero order when the reaction rate is, what option here are we going to go for? Where CA in this case means the concentration of the reactant. Do we need the concentration of the reactant when it comes to a zero order reaction? So look at the first guy. The first one they're saying is related. This means proportional. This symbol here means proportional to the concentration of the reactant. This means proportional to the inverse of the concentration of the reactant. This here means proportional to twice inversely related to the concentration of our reactant. The correct answer here is simply going to be D. That's the only sensible answer, because in a zero order reaction, the rate of the reaction is independent of the concentration. The concentration will never be part of the rate of the reaction, because there are no changes in the concentration of the reactant that are going to temper with how fast or slow your reaction is going to be happening. Yeah, so the only correct answer here that we can go for is D. Temperature will never affect the rate of a chemical reaction, because all the other variables are going to be kept constant, or they are standardized. Is this okay, guys, on question 2? Yeah, so that's what we have. Yeah, then you have the next one here, question 3. They're saying, in the following reaction of iodination of propane, there is an increase in concentration of ions. Which of the following techniques is not applied to follow the progress of the reaction? So this is what we are having. It's just a displacement reaction, because we have one hydrogen being displaced by an iodine atom. So which of the following techniques is not applied to follow the progress of the reaction? Which answer here, guys, is the best? So the correct answer here, yes, is D, because when it comes to calorimetry, which is just going to be the changes in your reaction, this guy that we're having here is a ketone. So ketones with halogen, the reaction is going to produce heat most of the times because of the iodine, and conductivity because the ions that are being produced. So ionic environmental conditions always has the conductivity part or properties. pH measurement, the hydrogen ions are being produced. So of course pH matters, because if we have concentrated hydrogen ions, meaning the displacement won't take place, we need to keep these guys in check. So the correct answer here is back titration. Why is this not part of the progression of these reactions? Because we know how back titration takes place. Back titration only happens when you have two particular experiments that you are running at the same time. The first one, let's say you have something like this, is going to produce something that will be needed in the second equation, or rather leave out something. In this case, let's say B won't be fully utilized in the first experiment. We need to combine it with, let's say, G to produce, let's say, D. We need two particular experiments, and sometimes they can run backwards. Here we just have one particular reaction, so this cannot be back titration. So this here is our answer. So you notice that they can also bring something that looks like it's general knowledge, just testing your knowledge on what happens in a lab overall. So this here, you've noticed the first part we did was about errors. That's what we did. Here now we're diving in to talk about chemical reactions, relating some certain features, identifying what could be wrong with the chemical reaction or what is happening. Look at question number 4. Question number 4, they're saying in an iodine thiosulfate titration, indicator is added at, because in this particular experiment where it's like we're utilizing starch, Yeah, so some people say at the end, because we need to see the pale yellow color that is going to be indicated to show that it's a reducing sugar or a non-reducing sugar. Yeah, but from the options that we are having here, we are going to say at the beginning of the experiment, unless if they gave us another option to say at the end. Yeah, Numez, what were you saying? Yeah, and this is mainly because in most cases when it comes to iodine thiosulfate, we're going to be dealing with reducing sugars. So that's the main reason why we deal with this. And the perfect illustration is when we're dealing with starch. Yeah, so how about this number 5 here? It's related to the previous question. They're saying color of starch iodine complex is, what's the color? You've done this experiment in biology. What's the color, guys? It's blue-black, right? Yeah, so it's a deep blue-black color. So the answer here is going to be C. This is correct. Then look at number 6. Number 6, they're saying in an experiment, it was observed that as the concentration of one of the reactants was doubled, the gradient of the graph was also doubled. The order of the reaction with respect to the reactant is what? You can guess this guy is here. What's the answer to this? This is under chemical kinetics. So you just look at the rate laws, the orders rather. In this experiment, whenever we talk about, you know what we mean when we say it's a zero order, right? Whenever you double the concentration here, or whatsoever you do to the concentration, it will affect the rate by a factor of 0. When we say something is a first order reaction, meaning if you double the concentration, this is 1. If you double this, the rate also doubles. But if this is a second order reaction, if you double this, it means the rate is going to quadruple. Yeah, so here the answer is going to be, it's a first order reaction. Yeah, because they doubled. Look at it's double. So it's like, think about it in terms of 2, 2. So what is 2, 2 reduced? Reduce this, meaning 1, 1. So meaning the order was just 1. That's how you should be thinking about it whenever it comes to the order of the reaction. Then look at number 7. Number 7, they're saying in an iodine clock reaction, if the time required for color change is too small, then the percentage error with respect to time is small. Is it true or false? So you have to understand the question first. In an iodine clock reaction, if the time required for the color change is too small, then the percentage error with respect to time is small. So they are saying if it takes less time for you to observe a color change, does it mean that the percentage error with respect to time is small? The answer is false. The lesser the time you have in terms of you observing the color change, the more accurate your thing is. It does not make it erroneous, no, it makes it perfect. Yeah, so the answer here is false because this statement here is wrong. It does not reduce the percentage error. Yeah, so the answer here is false. Yeah, obviously, I'm not sure how much of experiments you've done that involve iodine, but this is, according to this particular year, they had experiments involving iodine. So if you've done such, they'll bring something like this. But they'll always bring something that you are familiar with from one of the experiments, just a mixture of what can be answered or what they can get or extract questions from. Yeah, so yeah, you may not actually have something as complex as this. In case maybe you're wondering to say, why are they asking about iodine and starch and everything? We've not done this. This is because of this academic year. Yeah, so if they bring such a format as this, it may look like general knowledge, just testing your knowledge about reactions and a lab, so to say. Like look at number 8. Nitrating mixture is prepared by adding sulfuric acid to nitric acid with cooling, and the cooling is required because the reaction is what? So we are talking about an acid. Whenever an acid is involved, just note to say the reaction was exothermic. These are very explosive reactions, so we need to cool them off. Yeah, so the cooling is required because the reaction was exothermic. Then look at number 9. Number 9, okay, this I'll just skip it, but let me just, it does not apply to you, I think, in this year. I don't think there's a lab that involves it, but look at it. Benzene is harmful by skin absorption. Remember the first experiment that you did when it comes to talking about the errors in a lab, experiment number 1, identifying errors, things not to do, things to do. You need to protect yourself. Why do you put in a lab coat? They even put on the conditions for NS to say we need an acid-proof lab coat, right? Yeah. So they're saying this is harmful. A necessary precaution that is taken is why? What precaution can you take for something that is harmful to the skin, guys? Using a fume cupboard. Fume, if you're burning something, that's when we use the fume. That's option A. Using goggles, if you're looking at something like you're burning or something, that's when you use goggles. Wearing a mask, something that can be inhaled. It doesn't have to touch our skin. Goggles are for the eyes. Gloves are for the skin, our hands. So the correct answer there is B. Then look at number 10. The maximum question you should expect in a lab test is 15. That's the maximum. Yeah, so just expect 15 questions. And you should be able to do, if it involves you carrying out an experiment in terms of doing data collection, you have to make sure that you can do the data collection in 30 minutes so that you use the other 30 minutes for you to answer your questions, because the maximum time they'll give you, if not 45 minutes, they'll give you an hour. And please write your details at the beginning of the experiment on your answer booklet. It will be a one leaflet, answer sheet that they'll give you. Yeah, so because when time runs out, they'll just get it to my papers. So you need to have all the information written out so that in case you don't finish, at least whatsoever you're going to submit will have your details on. Your paper won't be lost. Yeah, question 10, they're saying eye protection is worn when? I look at the option they're giving us, the options. So A, when reactants are irritant, right? They can irritate your eyes. Reaction are endothermic, we don't. Activation energy is high. The reasonable answer here is A. Yeah, so you see that this is purely experimental general. The next one here says the titration reaction involving permanganate and ion does not require an indicator as the reaction is self-indicating, right? So this is self-indicate. It changes color. It changes from what permanganate should be, is it purple or blue, something like that. It changes and becomes colorless, the whole reaction when it's done. That's how you know to say the reaction has reached an endpoint. Yeah, so you have that type of self-showing or self-indicating that you are going to observe. Then look at number 12. When reading the burette, if the eye is above the liquid level, the resulting volume reading would be too small. Is it true or false? So if you read it, so they're saying above the liquid level. Is this true or false, guys? What's the correct answer here? What do you think is the correct response? Those things that have to do with the meniscus and everything else. Is this okay, guys? What's the best response here? Is it true or false? When we read the thing, it's true, right? Why is it true? Yes, because you're going to be looking at it at what we call it. Is it the angle at which you're going to be looking at it from is not going to be accurate. No wonder we try reading it at eye level. You need to at liquid level. So there are these diagrams. I'm sure you remember them. They are there. I think there are 3 things they show you in your lab manuals. They put a liquid like that. There is, I think, a drawing of an eye, reading it from this point, reading it at that point, reading it at this point. We prefer this point. Yeah, unlike this point. These 2 are wrong, so we prefer this guy here. So yes, this here is going to be true. Then if you have the next one here, they're saying in a basin burner, a bright blue cone is observed when the ratio of gas to air in the barrel is too large. Is it true or false? The explanation here is in a basin burner, a bright blue cone, inner cone, is observed when there is a sufficient air mixing with air gas, typically methane or natural gas. So when there's a sufficient air mixing with a gas. That's when we observe this. So here they are saying in a basin burner, a bright blue cone, when the ratio of gas is too large. No, so they have to be sufficient. They're supposed to be enough. Nothing should be in larger amounts or in lesser amounts. So here, no wonder the answer here is false. So false is true. Is a correct statement, I mean, response. Then look at number 14. Precision is a reproducibility of the results when several measurements of the same quantity is made. So it could be either a wrong outcome or a true outcome, but if you're able to reproduce it over and over again, meaning you are precise, whether the answer you're getting is true or closer to the true value or not. So that's precision. Being able to reproduce your outcome, meaning if you're making a mistake, you're repeating the same mistake here. So here the answer is true. Then number 15, the last one here, this is, you see, they make it interesting because they know it's the last one. So like I said, the maximum number you should expect is 15 of questions. But if there was some data collection we're doing, they make it at least to 5 or 8 questions. If there was a part where you need to do some data collection. But here, there was no experiment that we did. It's purely theoretical. You're just answering questions, showing us how best you know your lab, and this was carrying 15 marks. So here, meaning there are necessary calculations that need to be done. This is a titration, is it? Yeah, look at the question here. They're saying a sample of impure magnesium was analyzed by allowing it to react with excess HCl solution. After 1.32 grams of impure metals treated with 100 cubic centimeters of the 0.75 molarity HCl, the remaining solution required 50 cubic centimeters of 0.25 molarity of aqueous sodium hydroxide for complete neutralization. Assuming the impurities do not react with the acid, what is the percentage by mass of manganese in the sample? That's what they want us to find. So we're going to write the necessary equations that are needed. So first of all, let's come back to our question. This is just like a story. You have to follow it through. Yeah, so we're going to write the story here, the information that we're given here, so that we write the proper equations. So they're saying magnesium, impure magnesium was analyzed by allowing it to react with excess HCl. So we're having magnesium, excess HCl. This is supposed to give us what? Is it magnesium chloride? Magnesium is from what group, guys? Which group is magnesium from? Group 2. So meaning there should be a 2 here, right? If that's true, then here we're having the sodium hydroxide reacting to give us sodium chloride plus the HCl. This is what we are having. They did mention, so here they're saying impure magnesium was analyzed by allowing it to react with excess HCl. After, this is impure, the 1.32 is impure, so this is 1.32. This is the impure magnesium that we're having. This is the actual mass of the whole thing, right? The theoretical mass with impurities was treated with 100, so this is 100 cubic centimeters. Put the data there, there's 100 cubic centimeters. I can just divide it by 1,000 to put it in what? To put it in liters already. So this is liters. And the concentration is 0.75. So 0.75. And the question said HCl was the excess one, meaning it's the one that remained. So it just dealt with the impure magnesium, and part of it remained, and we dealt it, or rather completed it by 50, using 50. We used 50 here. So we used 50 cubic centimeters of sodium hydroxide, which is 0.25 molarity. We used this to deal with whatsoever HCl had remained, right? So is this a forward titration or a backward titration? Because the question they're asking about is the percentage of manganese. Is this a forward or back titration? That's the first thing you need to identify. Is it forward or backward, guys? It's backward because the information is asking about something that is in the first equation. So this is a backward reaction or titration. How do we know whether an experiment is a backward or a forward titration? The question that they're going to ask you, Are they going to ask you about something in the first or in the second equation? Because here, are you okay with how we formed our two equations? We have the first equation and we have the second equation based on the information given here. They said manganese, this guy here, just a minute, my screen is performing. The manganese, this guy here, hope you're seeing the arrow that I'm using to point here. So the manganese was analyzed by allowing it to react with excess HCl, right? That's the first statement they're giving us. Then here they're saying the remaining solution of what? HCl, because they said HCl was the one that was in excess. Yenze yambili. So meaning inasalako after tacha reactor magnesium. And the inasalako was dealt with. So the remaining solution required 50 cubic centimeters of 0.25 molarity aqueous sodium hydroxide for complete neutralization. For us to put a stop to this chemical reaction, we needed sodium hydroxide to finish off the HCl that remained from the first equation. Now they're going to ask us a question, and the question they're asking is, assuming that impurities do not react with the acid, what is the percentage by mass of manganese in the sample? They're asking about Mg, manganese. Manganese is found in the first equation, meaning we are coming back like this because they gave us two equations and they're asking about this guy here. So it's like we have to do reverse calculations. That's how we know to say it's a back titration. But if they were asking us about something in the second equation, let's say they were asking us about the volume of, let's say, a normal question, they would have not given us the volume of sodium hydroxide. They would have said find the volume of sodium hydroxide, meaning this is, we're coming like this, meaning that's a forward titration. Are you getting what we're saying? Have you heard what I've said? Aha, yeah, so okay, that's good if it's making sense. We're looking for the percentage of manganese. What we are asked about is found in the first equation. So we're going to start our reaction backwards. Yeah, so when we have, okay, so someone should please mute their microphone. Yes. So that's what is going to determine whether it's a forward or it's a backward. Yeah, so like I said again, so the same question here could have been a forward if they were asking about something in the second equation. Yeah, so if they were asking about HCl, how much HCl volume had remained, meaning tisakila ye nasal. So meaning we are coming like this, meaning yankala forward titration. Yeah, so according to this, I don't know how, but my battery is about to give up. So it's on what? This is... okay, it's on 10%, guys. So I'm just going to run you through the steps so that you're able to calculate this without my help. Yeah, so the first thing you're going to do, please take this guy down. I take the notes of what I'm going to be saying. Then you can confirm with me on WhatsApp because at least my phone is too full. So the first thing you're going to get are the moles of sodium hydroxide. That's what you're going to get using this information here. Make sure you change your volume to liters. That's step number 1. Then step 2, you're going to get the mole ratio between the sodium hydroxide and the HCl up. Tayambana equation 2. These guys are in a ratio of 1:1 in a mole ratio. So the number of moles you're going to get for sodium hydroxide will be the number of moles of hydrogen chloride. They will be the same because they're in a ratio of 1:1. And this number of moles you're going to get from step 2, you're going to call them the number of moles of HCl that were in the excess. Yana salako, the ones that we took in the second equation to react with your sodium hydroxide for the neutralization. So you keep them. These are the excess. Then you go to step 4. So I'm not doing the calculations, guys, because of my battery, but you can just take note of this. You go to step 4, you get the initial number of moles of HCl, initial number of moles in the 0.1 liter and the 0.7 molarity that you are given. So you get the initial moles of HCl. In the first equation, you get this. Because if you know what had remained, yet napeleka ku second equation, and the one that we had initially before the first reaction happened, we can now get the ones that reacted with manganese, the magnesium, which is just going to be, the ones that reacted is simply going to be the initial minus the excess. That's how we're going to do this. the initial moles are always going to be a lot. Yeah, so this will give you the number of moles of hydrogen chloride that reacted with the magnesium. We check the first reaction if it's balanced. Is this reaction here balanced? The first one, is it balanced, guys? Is it balanced? It's not, because we need a 2 here, right? Then a mole ratio of 1 to 2. Yeah, so you're going to do your mole ratios. So this is step number 6. Hope you're taking note of the steps. So you do your mole ratios between the acid. So this is 1 to 2, the HCl and the manganese. You get the moles of the magnesium, you get the moles. So you have the moles of Mg. Once you get the moles, you know, say number of moles is equal to mass and Mr, right? You get the mass. This is going to be like the actual mass without the impurities. That was the mass that participated in the chemical reaction. That's what you're going to get. And once you do that, you can now get your percentage yield, which is just going to be AY, the actual mass, what you've gotten here without impurities, over the theoretical mass, the 1.32, which was given, times 100%. Then you get your answer. This is going to be your percentage yield. So these are the steps that you need to carry out this, and the score of 15 marks that was given for the last part. So the answer you should get is 57.55% by the time you're done. Please make sure on using your periodic table, you use the correct molar mass for manganese, which is 24.3050 grams per mole, for calculation of your number of moles.